Hi, so in this lecture we'll start talking about motion control. So that's the ability to basically make your robot go where you want it to go. So far we've talked about tracking where it is. We haven't talked much about getting it to go to a goal location. So in this lecture we'll be talking about motion control, and we'll be looking at a simpler version of it. So no obstacles for now, and we're not going to worry about noisy sensors. We're going to always assume that we know exactly where the robot is at any given time. I'll start by reminding you a little bit about robot motion and kinematics. And then we'll talk about general high-level overview of what does it mean to have a goal pose or a goal position or orientation. Then we'll go through a couple of different versions of control to a goal pose. So specifically, if our robot is here, and we want it to be at some goal position, well, we'll have to remember some of what we've had from previous lectures. So let's say we have a frame here. That is our global reference frame. We'll have our local reference frame attached to the robot itself. And we'll define our goal. Depending on which frame is most useful, we'll define our goal in one of those two frames. And then, pun intended, our goal is then to have the robot travel to that goal position or pose. And I'll give you definitions for position and pose and orientation here in the next slide. After we've looked at a couple of different ways to do that, we'll talk a little bit about simulation. And actually this tracking will go down, under this bullet here. I actually reordered these last two and forgot to update this slide. And that will be your exercise. The first part of your exercise for this week will be simulating this motion here. So when I say motion control without obstacles or noise, let me paint that picture that I had from the previous slide. We'll have our global X and our globally defined Y and a globally defined origin at 0, 0. Our robot is going to have three parts of its state matrix, and those are going to be the pose of our robot. This little ball back here, as a reminder, is the ball caster. So something that just glides around the ground. And then we have our two wheels. This is our differential drive robot. Which is pretty much the simplest version of a robot that you could try to control. And it has its local coordinate frame. With X and Y defined for the local frame. This point here is the position of the robot. And our robot really just crawls around in that two-dimensional plane on the floor. So it's going to have an X, Y position. And we could define that with respect to the robot's reference frame, but that's really boring. Those two values are just 0. So we will define that with respect to the global frame. It'll have its X, Y position, its X position here, and its Y position here. Unless otherwise stated, we'll almost always have the robot start at the origin, and then as it moves around, we'll know its position with respect to some fixed position in the room. So we could pick one of the square tiles on the floor in 105 and say this is the origin, and if you're 5 centimeters forward from that, we know exactly where that is. So that's the position, but we'll also have an orientation. If I do a better job of having a horizontal line parallel with the global axis, our orientation theta is going to be measured with respect to the global x-axis, and it's going to be defined as the angle between the global x-axis and our local x-axis. So those two axes. That's how we're going to define theta. And so when I'm talking about a pose, I'm really talking about that 3-tuple. X, Y, both of those defined in the global coordinate frame, and theta. And just as a reminder, I'm not going to define theta as being part of the global coordinate frame because they are equal. So there's no reason to put the superscript. And without any subscripts, so by that I mean I don't have anything subscripted on the pose, we can define this as the robot's pose. And the syntax probably will look a little bit familiar from what we've seen before, because it's also the definition of the robot's frame. In this case, those two things happen to be the same because we defined the robot's frame, so these two axes and then the point here, we defined the robot's frame to be at this point, and now I'm also saying that the robot's pose is defined at this point. So this is one of those few instances where those are going to be sort of synonymous with each other. On the other hand, I could have a target location. And I'll draw that as another robot. And the reason I'll draw that as a second robot is because I want us to remember that the target location, or goal, I'll try to stick to the word goal, is the exact position and orientation that we want our original robot to be in. So both of those have to be true, both the position and the orientation. And I'm not going to group that together into a frame because it really doesn't make sense to call it its own frame. Instead, I'll just reference that as an X position in the global coordinate frame for the goal, a Y position in the global coordinate frame for the goal, and an orientation for the goal. So these three values here are our goal pose. So the notation gets a little bit messy here, but try to remember that the superscript capital G is for the frame. And the lowercase g here is a value for x. Just happens to be defined in the global coordinate frame. So any value for x, any value for y, and any value for theta. So sort of anything in this space. Or I guess we could have negative values as well. So the goal for motion control is to drive the two x values to be the same, drive the two y values to be the same, and drive the two values for theta to be the same. We're not going to do those three things separately, and in fact the control algorithms that we'll look at will affect all three of those values at the same time. And the last thing that I'll mention here is just to remind you that we're doing this without obstacles and without noise. So probably goes without saying, but I'll just mention it here. That means there's not some sort of obstacle here on the course that could get in the way of the path that we want to go to our target location. So no obstacles, and we'll always assume that we know exactly where the robot is, even though we'll see in a couple of weeks that that's not the case. Our sensors are imperfect, as are our actuators. Alright, well that's a good place for this first video to stop. In the next one, I'll give you a reminder of our kinematics model that we've developed for our robot.